The proposed X-fake framework evaluates the utility of simulated synthetic aperture radar (SAR) images by unifying a probabilistic evaluator and a causal explainer. The evaluator, constructed using a probabilistic Bayesian deep model, learns the posterior distribution conditioned on real data, quantifying the uncertainty of simulated data. The causal explainer, built with an introspective variational auto-encoder, intro-VAE, generates high-resolution counterfactuals, which are optimized with evaluation indicators and prior information to reveal the inauthentic details of simulated data. Traditional metrics, such as mean square error, MSE, peak signal-to-noise ratio, PSNR, and structural similarity, SSIM, are insufficient for SAR images due to their specific imaging mechanism. The Frechet inception distance, FID, is also unsuitable for SAR images, relying on pre-trained ImageNet inception networks. The X-fake framework addresses the utility evaluation problem by quantifying the domain shift uncertainty of simulated SAR images through a three-step process: constructing a probabilistic evaluator, PIVA, with a Bayes CNN model, pre-training an intro-VA model, and optimizing the latent code to obtain the counterfactual explanation. The probabilistic evaluator, built using a Bayes CNN model, captures the uncertainty of predictions by incorporating a probability distribution for its weights. The Bayes CNN network is optimized using methods like Bayes by backprop and Monte Carlo dropout approximation. The optimization problem is transformed into the latent space of the pre-trained intro-VA model, facilitating the optimization of the counterfactual explanation. The X-fake framework provides a unified, trustworthy, and explainable method for evaluating and improving the utility of simulated SAR images, outperforming other IQA methods in terms of utility. A Bayesian convolutional neural network, Bayes CNN, is developed for synthetic aperture radar, SAR, image evaluation and counterfactual explanation generation. The Bayes CNN is constructed using Monte Carlo dropout and local reparameterization trick, approximating a probabilistic deep Gaussian process and optimizing the variational posterior distribution. The network is trained to predict category and azimuth angle of SAR images, along with their corresponding uncertainties, calculated using category uncertainty and azimuth angle uncertainty. The research proposes utilizing intro-V, a probabilistic generative model, for counterfactual explanation generation. Intro-V consists of an encoder and decoder that project high-dimensional data into low-dimensional latent space. The counterfactual explanation generation involves optimizing the latent code Z to minimize distance constraint, prior category and angle information, and predicted uncertainty. The optimization is performed in the latent space using the pre-trained encoder of intro-V. The paper evaluates SAR images generated by advanced generative AI approaches, including SARACGAN, SARC, and SARN-ERF, using a novel evaluation method that does not require paired data. The proposed evaluation method utilizes a Bayes CNN model trained on real MSTAR data, which is then used to evaluate simulated data. The results show that the proposed method outperforms other full reference and non-reference IQA methods in terms of utility. The paper also explores the effectiveness of different Bayes CNN models, including EVA-BBB and EVA-MCD, and demonstrates that EVA-BBB can achieve better performance in evaluation. The recognition versus substitution rate curves, RSC, are presented as a dataset utility evaluation index, illustrating the global utility of the datasets. The proposed method can successfully assess the simulated SAR images in terms of data utility, even when they have similar visual quality. A novel explanation method is proposed to evaluate data utility for each sample with a quantitative metric, enabling the filtering of high-quality data. This method explicitly reveals inauthentic details of simulated data through visualizations of original simulated images, generated counterfactual samples, and explanations of inauthentic details. The counterfactual explanation improves data quality and utility both explicitly and implicitly. Quantitative experiments verify the effectiveness of the proposed method, demonstrating that training with full original simulated data causes a dramatic decrease in classification accuracy, while the generated counterfactual explanation can improve data utility. The method is effective in improving the utility of various deep learning architectures, such as ResNet 18, ResNet 50, DenseNet 121, and SWIN Transformer. Ablation studies confirm the effectiveness of each module in the counterfactual generation process, showing that the recognition model trained directly on original simulated data and tested on real data obtains a baseline result. The counterfactual explanation method, using VAE as the generator and optimizing with distance and uncertainty, shows a slight improvement over the baseline. The addition of class guidance and intro V further improves the utility of the generated counterfactual data. The proposed framework, X-Fake, comprises a Bayesian convolutional neural network-based probabilistic evaluator and a generative model-based causal explainer. The predicted uncertainty of simulated data reveals an inconsistent distribution with real ones, serving as a criteria for utility assessment. The counterfactual explanations are generated with prior information, including the target label, azimuth angle, and predicted uncertainty from the evaluator. Experiments demonstrate that the proposed evaluator can filter out high-quality data, and the trained deep learning model can achieve higher performance on real SAR images. The generated counterfactual images explicitly improve the utility of simulated data, with the classification model trained on generated counterfactual images outperforming those trained on original simulated data by 30%. A comprehensive review of image quality assessment, uncertainty quantification, and Bayesian deep learning methods is presented, highlighting the importance of estimating uncertainty in image quality assessment tasks. No-reference metrics such as BRISQUE, NIQE, and PIQE, as well as reference-based metrics like PSNR and SSIM, are cited as essential components of image quality assessment. Uncertainty quantification methods, including Bayesian neural networks, dropout, and ensemble methods, are discussed as crucial for deep learning models. Bayesian deep learning approaches, including Bayesian convolutional neural networks, Bayesian neural networks with variational inference, and introspective variational auto-encoders, are reviewed, emphasizing their significance in SAR image generation and target recognition tasks. Image denoising and despeckling techniques, such as preprocessing filters and discrete wavelet transform-based noise reduction, are also discussed, highlighting the importance of variance stabilization and non-local filters in SAR image denoising. The authors emphasize the need for probabilistic perspectives on generalization in deep learning, citing studies on Bayesian deep learning and uncertainty quantification. They stress the importance of further research in this area to improve the reliability and robustness of deep learning models in image quality assessment and SAR image analysis tasks. The review underscores the significance of uncertainty quantification in deep learning models, particularly in image quality assessment tasks, and highlights the potential of Bayesian deep learning approaches in addressing these challenges. The discussion is supported by various studies, demonstrating the importance of uncertainty quantification and Bayesian deep learning methods in image quality assessment and SAR image analysis. The author's review provides a comprehensive understanding of the current state of research in this area, highlighting the need for further investigation to advance the field.